This lesson goes over how to model different types of equations using a balance scale. First, we need to really understand what the equal sign in an equation means. The equal sign simply means two things are the same in some way. So for example, if I said Mrs. Devers' weight is 135 pounds, what that means is that if you were to put me on one side and a 135-pound weight on the other, the two things would be equal to each other. That word is often translates to an equal sign. You can imagine a balance scale, and that these two things, me and the weight, would balance each other out perfectly, and that scale would be level. If we were to write a pseudo-equation for this, we might write Mrs. Devers' weight equals 135 pounds. The equal sign simply says the two things balance. We can also balance things that don't have weights, but that have, for example, values. The cost of 2 tickets to a movie and a box of popcorn is $24.50. So we could imagine setting these two things equal to each other and putting them on a balance scale. And while they might not weigh as much as each other, their costs balance each other out. Again, we can write a pseudo-equation that says 2 tickets plus 1 popcorn is equal to $24.50. If we wanted, we could turn that into a slightly more algebraic-looking thing where T stood for the price of a ticket and P stood for the price of popcorn, and we could say 2T, 2 times the price of the ticket, plus P, the price of the popcorn, has to equal $24.50. We could imagine taking a very large balance scale and stacking yaks on top of it, just because stacking yaks is a fun thing to do. So if we were to take 3 yaks and stack them together on one side of a balance scale, if that equaled 1,200 kilograms, then the scale would balance perfectly, but the yak on the bottom might not be very happy about that. From looking at this balance scale, you could quickly tell how much each yak would have to weigh in order to make this balance. If 3 yaks equals 1,200 kilograms, you can figure out in your mind how much each one yak must weigh. We could turn this into an expression with a variable again by saying 3y equals 1,200, and we could solve this for y by dividing both sides by 3. Typically, we're not going to be dealing with yaks or teachers' weights. We're just going to be dealing with the algebra itself. So here's what balanced equations look like if it's just algebra. 2x equals 10. How could we draw a picture of this on a balance scale? Well, we could have a scale that on the left-hand side has 2 x's. You can think of x as like a mystery box. It's a weightless box that has some number in it. We don't know what the number is, and our goal is to find out how much has to be inside that mystery box in order to make the scale balance. You can tell from looking at this one that each x would have to have 5 in it in order to make the scale balance. We could also show 10 as a single quantity on one side, or we could break it up into 10 individual ones. Sometimes it's helpful to break that 10 up into 10 individual ones when we need to take some small number away from one side of the equation in order to help it balance. If we have an equation that looks like this, 3x equals 600, what do we do with that 3? Well, that 3 is a coefficient. It's telling us how many x's we have. So there's 1, 2, 3 x's. Notice that there is no number 3 on the side. There are simply 3 copies of the x. And that balances out with 600. In order to make this scale balance, each x must be worth 200. What if the stuff we have on the left-hand side has different kinds of terms? What if it has both variable terms and constant terms, like this equation? We can build that fairly easily as well. On the left-hand side, we have 2 x's, so a single x and then a second x. We also have 3. I'm going to show that as a stack of 3 ones. And that balances out on the right-hand side with 9. I showed that as a stack of 9 ones. You can imagine the steps that you could take to figure out how much each x has to be in order to keep this scale balanced. Sometimes we have equations that involve the distributive property, and it's worth looking at how we model those on a balance scale. Let's start with the stuff that's inside the parentheses first. So x plus 1, if we build x plus 1 on our scale, here's what it looks like. There's an x and a 1, and they're together. That's the x plus 1. The 2 on the outside of those parentheses means we have two exact copies of the stuff inside. So we have a single x plus 1 and then a second x plus 1. Notice that we don't have any parentheses sitting on our scale. Instead, we've used the parentheses to decide what thing we should build two copies of. And then on the right-hand side, we would build 8. Sometimes we'll have equations that are going to require combining like terms, and our balance scale can help us see which terms we can combine. So here's an equation, 2x plus 3 plus 4x equals 9. So let's build this on our scale first. Here's the 2x, then here's 3 more, then here's the 4x, and then on the right-hand side that balances with 9. So a reasonable question is, how do we see combining like terms as moving things around on this scale? Well, here's our scale that we had built before. Notice that we have on the left-hand side a 2x and a 4x. We have a whole bunch of x's. We can rearrange the things on the left-hand side of our scale without unbalancing it. So I could take the 2x and put them right next to the 4x. When I do that, I see that altogether I have 6 x's. I've combined my like terms. I still have to keep the 3 on the left-hand side. So there's my 3 ones, and they stay. And my 9 is balanced on the other side. So you can see what combining like terms looks like. Notice that we couldn't add together the x's and the 1's on the left-hand side because they're not the same thing. They're not like terms. So when we combine like terms in this, we get 6x plus 3 equals 9. This is the end of this set of notes. If there's anything that's still confusing to you, put a little question in the margin of the notes you've taken so we know to go over that tomorrow in class.